so many things.
Okay, is that it?
Anything that it seems like I'm gonna try to like check to see if you're being honest, I don't do. So I just assume.
And different.
And I know this one little thing that if you're not, and I'm not saying anything about anybody, if you're not, it'll just come back to bite you. You know, there's one of those things I don't need to do anything whatsoever.
So I figured.
No, I don't like to, I'm not gonna read the code.
I was not able to figure out.
Don't waste your time. You'll make my old GTA very happy.
Not doing okay, you can send me. Yeah, sure. Please tell me how to get my code right.
Okay, welcome back everybody. I'm going to put these questions on the board. There's a few of them that our esteemed colleague over there has asked us. So I'm going to discuss them. So one, could we talk about an overview of characteristic functions? I'll say something about it, if you'd like. So no problem. Sim study to estimate the mean of a beta prime you probably never hear of this distribution outside of this class. I didn't even know what it was when I originally wrote the question. And then I was like, oh, this is like a distribution that people know the name of, and there's a Wikipedia page. So, cool. And problem 4. I'll say something about it. Anything else anybody want to discuss? Okay, I assume we'll keep it conversational because this is going to take me 10 minutes. So these are the questions. Anything else we should add to the queue? Comments, concerns? Characteristic functions. So Eric, no, I'm not going to do the derivation here, but it can be done. You specifically mentioned the Cauchy, so I'm thinking, if I can anticipate your question a little bit, you're wondering if that's what you should have done on the midterm. Maybe?
Maybe.
Okay,
I
so
came across it when I was figuring out how to understand. Yeah.
some people did that and they know their characteristic functions off the top of their head. I'm not sure how that's possible, but for the midterm question where I asked what distribution does some of the xi's over n follow if the realizations come from a Cauchy? All I was doing on that problem was checking to see if you read the book. Because right after it goes through the central limit theorem in its derivation, it says doesn't work for Cauchys. It doesn't even fill out the whole problem. So it starts doing a transformation of variables. So all you need to do is apply that. If you like to use the convolution formula for adding together things, if you like transforming a different way, I assure you they're equivalent. So you could do the direct transformation there. And they say in the book you'd have to solve partial fractions problem. And I'll assume you guys could teach that to yourself if it was essential. I'll never ask a question where I actually ask or expect you to do that. All I wanted you to say was central limit theorem does not apply here. And a lot of you guys, at least half, got caught on that. So now there are some other answers that said something, and you get like -5 or -6 if you said CLT applies and you started saying it's normal. I just wanted you to realize that is not true if the variance doesn't exist. And that's the underlying condition for the CLT to hold, regardless of how you prove things. If you wanted to prove that and it's super surprising, if you average over Cauchys, it's still Cauchy 0,1. So Cauchy 0,1's averages are Cauchy 0,1. So it doesn't even reduce the scale. So it's not 1 over n or anything like that. I think I saw that answer once. It's reasonable to think that. But Cauchys are very neat distributions that their averages do not reduce the variability. And it's because those tails are thick. And they're really thick, and I use them all the time if I want to alleviate some of the burden of outliers. You know, I like to see that that doesn't follow the trend. Normal tails can't pick that up, and I have ways of doing that. And if you take my maze class, I'll walk you through some of those exercises. So I think that's just kind of interesting. Again, I think it's a very good idea if you guys read your book. Work the practice problems, and I promise you, if you don't, I will find out. You know, because there'll be something that's bizarrely difficult if you hadn't seen it in the book, and it's bizarrely simple if you had read the exercise and tried to work through it. So I still want you to do all that good stuff that people do. Read their book. You asked a different question. What are characteristic functions? I'm not going to work through it on a code sheet, but for T distributions, code sheet belongs to that family. Characteristic functions exist. Moment generating functions do not exist. And that's good, I guess, because T's don't, or I should say Cauchys don't have any of their moments. So a T2 has a little bit, some moments. Does anybody know what they are? Which ones exist for it? So a T1 is a Cauchy, no moments. A T2?
Everyone has a mean but not a range.
Very good. T3s, how many moments exist? 2. So a Tn has n minus 1 of their first moments. In that order, they exist. So MGF, if moments don't exist, and I'm going to try to wean you off of always thinking about means, and this exercise for the simulation study is supposed to lead you in that direction. Maybe we shouldn't be thinking about means all the time. But maybe we shouldn't always be thinking about moments. The proof we did in the class required the MGF, and it's because it's the easiest proof. And again, I don't really, you know, I wouldn't like you to know that the CLT applies for finite variance. We're not going to do a proof like that. It would take quite a long time to go through measure theory. And I imagine if you do see a more sophisticated proof, they might assume the first 4 moments exist, and all you have to do is assume the second moment exists, and that proof's quite a bit easier. The reason I know this, I got a lot of books on my bookshelves at home, here, and I read them. And sometimes this stuff is in there. So good on you for taking the extra effort and reading through things and getting curious. A moment generating function looks like this, e to the tx. And you know what that means. It's e to the tx. I'm assuming that x is continuous. If you want to change the definition of my integral to a discrete case, that's fine. It's just notation. Right? Integrate over x. All of x. So x isn't part of that equation. And that formula you can use to derive all the various moments if they exist. So if you're missing some of the moments, I don't mean they're 0. I mean that they don't exist. You won't be able to do that integral. And so what happens in an integral when you can't solve it? Think about this function right here. E to the tx, what is it doing? It's getting big. It's blowing up. And so if the tail behavior for this distribution isn't coming down fast enough, this thing will override it and it'll shoot off to infinity. And so that's a problem. So if you wanted to describe things using their moments, it means that all the moments don't exist. So a characteristic function is similar to this. By the way, this is also called a Laplace transform. So if you've taken a differential equation class or something like that, or you're an electrical engineer, you would have encountered this a little bit different. They probably wouldn't say this is the expectation of something, and they wouldn't require that to be a probability density. So these are useful in all kinds of fields. The characteristic function has the imaginary number right here. And the imaginary number is the square root of -1. And if you don't know a lot about complex calculus, there's no point in talking too much about it. But basically the calculations work out exactly the same. So same sort of calculus. You probably need to be familiar with the imaginary plane. But let's just give you some insight on this right here. Like, what is this? It's not any more imaginary than the real number line. It's exactly the same thing. So all these ideas are abstract. They're just abstractions. And so things in the imaginary plane live in 2 dimensions. And so I don't know if you know that, but just real quickly, this function right here geometrically, what is it to you? Kind of just probing you to see if you've had any experience with complex.
Rotation.
It's a rotation. It's a circle. So this is a circle. And so some people write this out is cosine tx plus I sine tx. So it's an expansion into sines and cosines. And if you took a complex analysis class, or if you decide to one of these days, because it is kind of interesting. I don't use it too much, but I know a bit about it. I've taken a class like that before. I thought it was kind of fun. But what does this thing look like? It's a circle. So if we're thinking about these as axes, so this is the first, this is the x-axis, if you like to think about it that way. And this is just telling you, here's a two-dimensional part. And so that's this part of the axis right here. And if you start thinking about it geometrically like that, instead of trying to plot this in one dimension, but if you plot this in one dimension and you plot that other part in another dimension, this is what a circle looks like. So you can kind of start to see that just by going through second grade and learning what sines and cosines are. I'm not sure when we actually learned that stuff. I don't remember. Probably not second grade, right?
No, I don't think so.
It's a metaphor. So, a long time ago we learned something about it. But if you ended up plotting a function, the cosine of x, and you plot it as its second dimension, the sine of tx, that is what a circle looks like. So here's the neat part, is doing this and taking the expectation with respect to the circular shape constrains everything. So things that blow up in the continuum, they'll explode. This bounds them by constraining everything to a circle. So that's at least a little bit of geometric rationale. Eric, I think that's all you need to know for now. So take a complex analysis class later on in your career if you want to fill in some of these details. If you find that you're like, I'm a probabilist, and I really like the math, you'll be into this stuff. Is it useful? It's also useful. So people that do acoustics or signal engineers, so some form of a mechanical engineer. Do we have any of those in here? No. They'll study this all the time. They don't call it the characteristic function, but they do operate like this right here. They do this integral. It's called the Fourier transform. And so one of the big applications of Fourier transforms is instead of talking about the function as something that's kind of going up and down, a signal, you could talk about what the frequencies are and decompose everything. And I'd have to teach you a lot more, but you can use this transform to pull out the frequencies of all of your signals. So if all of a sudden the E and the G were ringing really hard out of a guitar or something like that, those pertain to a certain number of kilohertz. I don't know what they are off the top of my head. I think E is like 450 kilohertz. Something like that. Is it 40? Okay, so 40. So I think my kilo in your, so we're off, but about 400. So sometimes I see people say, tune your guitar to 455 or something. I think you mean 45.5. I don't know that much about it. So I don't study the theory on that kind of stuff. I just see it every once in a while. But these can exist when moment generating functions don't exist. And so T's have them. I'd have to teach you about Bessel functions, have something to do with gamma functions. So to derive all of this. Let's say if you want to know more, look at stack exchange or something, but probably wait until summer. So because it's not going to help you in this class, but good thing to ask about. So this is Fourier transform. So Fourier has he's posited something where he said every smooth function can be characterized by a basis expansion of this right here, sines and cosines. What I mean by that is they kind of change the frequency and they'll offset this by like a k, and they'll look at something like this. Sum over k is going to do some number of modes right here, and there's going to be some coefficients, alpha k, and I'm going to write it like this, beta k, and I'm going to get rid of the imaginary thing. And so signals that are going up and down in really weird, complicated ways, but there's a period to them, they can be characterized by an expansion like this. It kind of smacks of what Taylor said. So Taylor had a condition on things being smooth, i.e. the derivatives needed to exist, and Fourier's representation is a little bit more general. So, all fun things. That's all I want to say about that. So, things for the future. I do use this sort of stuff when I'm modeling, and so I don't describe it this way as a characteristic transform, but sometimes where I have seasonality in things, I'll use this sort of expansion and try to pick out the coefficients that model whatever it is I'm doing. If you want to see some of that in my literature, you go to Google Scholar and probably check out my epidemiological work. So I have a good StatMed paper where I did some stuff with this once upon a time. And so I think a lot of our understanding comes through experiences and projects. Okay, so let's just get rid of that. That's all aside. Sim study to estimate the mean of a beta prime. You could do it that way, and I think I'm kind of prompting you to do it that way, just so that you can learn a valuable lesson. If you do Monte Carlo to estimate the mean and the variance, your code will run thousands of times slower. So, and I like doing that. So if you take any of my classes, I do that periodically. If you ever find yourself in that situation, it's either because you can't do anything better than that, or because there is something better to do. And I just want you to experience it and remember. What you would do is, what I might do is I might take Pi and get it from its posterior distribution. So these are the P's in the example that we were studying. So this is that Bernoulli beta problem that we are studying. So if you ended up working out the posterior distribution is a beta, and it has a couple arguments. Alpha plus some of the xi's. I goes from 1 to n. And the other argument is beta plus n minus some of the xi's. And we've derived this posterior. So what it means is that my posterior distribution on P, given all of my data, the sufficient statistic right here is some of the xi's, so I could either write this down using all the x's. I usually do it that way, but if you condition just on some of the xi's, that's the only way it creeps into this formula. It looks like this: P to the alpha plus some of the xi's, 1 minus P to the beta plus n minus some of the xi's. And I can rewrite this. I'm just going to make a definition. This is P to the alpha tilde, 1 minus P to the beta tilde. So this is alpha tilde, and this is beta tilde. So it's just another beta distribution. That's what conjugate priors do. Prior was conjugate, it's beta, so the posterior is beta. What a Bayesian's doing is just updating those parameters based off of the data that they've seen. The beta prime is a transformation of variables of this thing right here. So I don't need to know what the kernel is, or I don't need to know what the normalizing constant. All I need is the kernel, and I can do this transformation. So if I wanted to transform, I'll say z is equal to p over 1 minus p, and I do this transformation. Keep in mind, we're now operating as Bayesian, so the probability distribution is on the parameters that you're trying to learn. So I can transform that distribution. What I need to do is I just need to back solve for z, p in terms of z. It's going to look like z over 1 plus z. So you've probably checked that out already. And then I'll need to come up with a Jacobian of all of that. And I could transform and find this distribution, the beta prime. Now what I can do, and this will have these parameters in here. And in fact, they'll be exactly these parameters. So the beta prime is defined in terms of the exact same parameters that define the beta distribution. And they have the exact same interpretation. So What I could do is I could sample a heck of a lot of times out of this beta distribution. So for each nested simulation, so for an NP configuration, I'm going to get data. That data will give me the sum of the xi's. What I could do is I could go, and I'm going to call this J, just so you don't get confused with the notation. PJ is distributed beta. It means that it has this shape to it. What I could do is I could go to a beta simulator. So they'll have one in R4U or MATLAB. Any package will have this for you. Standard distribution. And I could just sample a heck of a lot of times. So I could get P1 all the way to P, and I'm going to say cap J. This is going to be some really big number. And from those, I could take Z1 and define it to be P1 over 1 minus P1. Z2 is P2 divided by 1 minus P2, so on and so forth. So Zj, myself some room there, is equal to Pj, 1 minus Pj. So this is the beauty of Monte Carlo. If I didn't know that this was beta prime, if I drew a histogram of all of these samples, they would not look like those. So these follow a beta distribution, these follow a beta prime distribution. So what you could do is just sample a heck of a lot of times from your beta distribution, transform all the samples, and then I could approximate the mean using the empirical mean. Meaning that I would just come up with Z bar. It's going to be these ZJs divided by cap J. J goes from 1 to cap J. And so you use a mean like this to estimate a mean. If I wanted to compute its variance, I could use those discrete samples and come up with a very close approximation to the variance, or anything you wanted. And so for a lot of people out there, the name of the game for them is being able to sample quickly from distributions. They don't know what the distribution is. Usually in 1D, people could figure things out. But in high dimensional spaces and whatnot, for complex models that you've built, you might not be able to do all the calculus right away. You might not ever be able to do it. And so you can just use samplers and then come up with estimates from that sampler. And I could just crank up J as big as I wanted, depending on how many decimal places I felt like estimating something to. And so that is, if I let J go to something big, and I computed this right here, I'd say this is Z bar, is what I mean to say. And then I repeated it again. I went and sampled cap J really big again, and I computed Z bar, and they were equivalent up to 1 decimal place, but not 2 decimal places. It looks like you're not estimating that second decimal place very accurately. And so what you would do if you're interested in reporting that is you would crank up J and do it for longer. One thing that you'll start to see is you'll see, young assistant professors or people that are coming in that are aspiring to that. They'll have all their simulation results cooked up, and they'll have them all in tables with like 9 decimal places. And I'll always ask, how accurate do you think those are? And I don't know, I didn't check. I assure you, estimating something in 9 decimal places is extremely difficult. How big would cap J need to be? Bigger than the number's bigger than you can even think of. So it's not a number you know the name of. So calculating something at 6 decimal places is pretty difficult sometimes. So that's how you operate all this in Monte Carlo land. So just so you know, there is another variant of simulation study called Las Vegas simulation instead of Monte Carlo simulations, Las Vegas simulations. It's a little bit more mathematically involved that you say, I want to be within 3 decimal places, so you'll set your tolerance, call it epsilon, and you'll say, and this is the hard part of this, you'll say probabilistically, I want to be within that tolerance with probability 0.9999. So it's not even a guarantee. It's just like pretty sure that I'm within that tolerance. Those are called Chernoff bounds. I did get a chance to meet Herman Chernoff one time. He asked me a question in a colloquium. It was the highlight of my statistical career. So if you've ever studied the history of statistics, he's one of the big players. He's the one that came up with the faces to describe data. So he says there's 16 different faces. It's kind of like your personality profile or something like that. He applied this idea to data. It is the clumsiest thing I've ever seen. And everybody seems to remember him for that, but he did a lot of high-powered mathematics too. So I'll let you just keep that in mind. So the caveat to that is your running time on everything is random. So if somebody's like, how long is that simulation study going to run for? You'd say, I don't know. Could be done in a minute. Could be done in two. And so it's, for this sort of problem, it's going to estimate depending on the size of P. You know, if P is really small or really big, it's harder to get a good estimate of it. And so, if P is small or P is big, you might have to run this thing for some unknown quantity of time. It takes a long time, and people don't like that. So the engineering way of dealing with this is just cranking up J, rerunning it a couple times, and seeing, you know, if your estimate is stable. Anything you want to estimate or anything you want to report, you should run your simulator long enough and make sure that you're estimating it accurately. People don't like to study Monte Carlo error. So, okay, so that's how you would do this simulation-wise. But it turns out I know something. I know that the mean, this thing right here, is going to be approximately, so I'll write it right here. This is approximately alpha tilde over beta tilde minus 1. Do you know how I know that? Yeah, I went to Wikipedia before when I saw your question. What's that?
It's not on your hand.
No, I said to a student I would send him an email, which I did. So, with some information they wanted. So it's not there this time. I could remember that. And so this is kind of interesting. So what you would do is go to Wiki, type in beta prime. It'll give you the mean, the variance. It'll tell you when they exist or not. The worst thing you could do with Monte Carlo is try to estimate this, and it doesn't exist, so it's just jumping all over the place. You go, I have an error in my code, but actually it's doing exactly what it should and not converge to something, because sometimes the mean doesn't exist. This has to have it so that beta prime is greater or equal to 1. Greater than 1, in fact. So that's this number right here. So beta prime is just this thing. So this has to be greater than 1. The prior I recommended was a half, so there's no guarantee. This thing's always going to be positive. But if you don't see at least one failure in this, so if it's 0 failures plus a half, that quantity will not exist. And that's the mental exercise. A Bayesian has a solution. They could either crank up their hyperparameters. So here's a really, and I would want you to just comment on this if you do take the easy way out. If you said, well, I'm just going to make my prior different, and I'm going to crank it up so that there's alphas at least 1 or betas at least 1, is you're going to bias the result quite a bit. Your prior has more weight in there. And you can kind of see the influence just by studying these parameters, how the data in the hyperparameters relate to each other. And in the transform, if you want to work through that, they have it in Wikipedia. You can just make sure you get that same PDF function as a good mental exercise. So you could crank up your hyperparameter and control this. What I say is, why not just report something totally different? Now I understand you guys have 2 objectives in this class. Objective 1 is to learn lots of things and explore lots of things and build up all your experience. And objective 2 is to make sure you have enough time for your other classes and all your other responsibilities, and on Sunday, Claire needs your time. So what that means is that you might take a shortcut. I know that I'm not going to fully answer this question in its full-blown glory. I'm not going to report the mode. The mode is more stable than the mean, and that's what I probably report, is just report the modes. The nice thing is that an apples to apples comparison if I compute and I compare to the delta method? And I would say yes. Because in a normal distribution, the mode and the mean and the median are exactly the same. And so the mean that you're trying to report that might not exist in the delta method, it might coincide with the mode of the Bayesian's analysis. And so I think it is fair to compare those things because the delta method is trying to tell you about modes or something like that. It's just that sometimes that delta method approximation doesn't exist. And it will just fail, and how do you fix it? There is no way you can fix it. You're just dead in the water with it. It does work okay as n gets bigger. And so you're supposed to realize that and make note of that. Instead of computing variances, another thing that might not exist, what I said, maybe you're interested in comparing coverage rates or something like that. So for the Bayesian, that seems maybe a little bit strange that I can still compute a 95% interval. So a beta prime distribution, it's going to look like, this actually looks kind of smooth. So it's going to look like something kind of smooth if you end up just chopping off the 2.5% tails from that distribution. So look at the quantiles of that distribution, you could come up with that HPD. A simulation-wise way of doing that would be to compute all these Z's. Same thing, you'd simulate all these P's if you didn't have a beta prime simulator. You don't have a beta prime simulator in R. But you do have a beta simulator in R, so you can just build your own beta prime simulator just by doing the direct transform. What you could do is you could order all of those samples and then take the, let's say you've computed 1,000 of them. So what you would do is you would compute the 975th quantile and the 25th quantile by just looking at the 25th biggest point and the 975th biggest point. And if I have those 2 points, I would have a 95% credible interval. That's the way Bayesians call this. You could check its frequentist performance and see how often that covered. So just because you're a Bayesian doesn't mean you wouldn't be interested in something that has a frequentist interpretation. So I might do that, and then I could do the exact same thing with the bootstrap or the delta method and say that I'm monitoring coverage rates and see how often they cover. So what I would say in that case for reporting information and just making like the explanation of how well these methods compare to each other, if the delta method failed, I would say it didn't cover. So now I can compare apples to apples across the board. And I could do the same thing for bootstrap. There's other ways out of this. You could say, I'm going to augment my data set. And some classicists do this. There's no mathematical justification for it. But they might say, I'm going to add a success and a failure to all of my samples. If you're bootstrapping, you'd have to do that after bootstrap replicate. So, because there'd be no guarantee. That biases the results as well. So Alan Agresti gave us that tool a long time ago. Kind of funny, I was having dinner with Alan Agresti a long time ago, and he said to me, everybody knows me for this silly tool, but I've done a lot of really hardcore stuff, and everybody always cites me on this. And it's very similar to taking alpha and beta and making it 1. Because if you think about how this appears in the Bayesian analysis, is it's just getting added into the successes or the failures. So there's kind of a way that you could compare these two things and justify that they're similar. That's what I want you to get out of this class, mostly. I want you to learn all the probability calculus and work all the problems and be able to do all that stuff. Statisticians that can do that are just totally useless to me. You know, it's when they can do that and come up with explanations and apply things. That's when they're useful. So, and that's what we want to create here in this program. So I'd like you to think through those issues, but also think about your limited amount of time, you know, and what you want to report. Let me just say one more thing about this. For the sim study, probably like something you'd want to report, whether or not it's a mean or a median or something like that. Let's say it's the mode, might be the mean and the delta method thing. And if I wanted to compare everything, I'm going to make some plots. And here's how I would probably plot it, is I might say, so just real quickly, what's bigger, N or P, the number of iterations you have to do. So I have P chopped up into 7 things. I have N chopped up into, how many? 4. So I would probably let this be N, a plot for each N. So I've got like a 30, right?
Yeah.
And I picked that for obvious reasons. I probably should have picked 31. So, not sure what point I would be making. And I might let this be P is equal to 0.01, right here. And so in this plot, I might have 3 different box plots. So maybe this is for your mode or your mean or something like that. I might have 3 different box plots for the 3 different methods. I don't know that they would look like this. So the box plots have these little whiskers right here where it takes the samples, it looks at the interquartile range, it plots it right here. The little stuff in the middle is either the median or the mean. And sometimes you'll see plot both where the diamonds are showing you medians or something like that, and a little line through it is showing you the mean. You have to always look up what they're reporting to you. And the length of the whiskers, I would say don't worry about it, because every software package out there does something different. I've heard from lots of people, oh, it's always 1.5 times the interquartile range. But then when I go to different software packages, there's all kinds of defaults, and it does all kinds of weird things. And even in MATLAB, it will say that, but I assure you it doesn't always do that. So be careful with that. It's just a visual tool. So it wouldn't be good enough to just plot this right here, because I wouldn't know which method is working best. So what I would want to know is what's the true mean for everything. And so what would the true mean for this process be? And I would probably plot that in here. So, and show you maybe what the true mean is. And then I would visually just describe what's going right here. So this might be delta method, this might be bootstrap, and this might be Bayes. My Bayesian procedure. This might be my expectations. If I did pick expectations, some of the expectations wouldn't exist. You'd have infinities, and if you try to plot that, it will blow up. So what I would probably also do is to note that this is based off of maybe if you repeated this, how many times do I say to repeat it? 100. So you might say, oh, this only had 58% of the times the method worked. So I might plot that on there too, and say when it works, it seems to do okay. And then this might be, 86% for bootstrap. You'll need to tell me a little bit of the things you do. But if I were a grad student, I would be thinking about how do I do the exercise, get what I want out of it, but also make it so my write-up doesn't take forever, So I'd be doing this joint optimization. Maybe the Bayesian method, 100% of the time it works, but maybe it's because you biased it a ton. And here you'd say, well, it's pretty biased. The box plot barely ever overlaps what the truth is. So for all of that. So how do you know what the truth is, by the way?
P over 1 minus C.
Yeah, you've got it right here. P is equal to 0.01. So all of these, the truth exists. It's just the data might not be able to give you enough information to learn about the truth if you define the truth as expectation. Again, lots of open-ended things you could do. Then you might do the same thing over here. For P is equal to 0.1, you'd have your 3 box plots and just report how well they work. And then I would do this for my 7 configurations of P. The reason I did this for P going this way and this pertains to n is equal to 30 because I'll have less plots. And so these are called side-by-side box plots. In my experience, in order to get it to do this, I have to change the code to the side-by-side box plot a little bit. And people have code for that on Cran's website. There's a MATLAB repository as well. So half the exercise is being able to just report sensibly your conclusions from a rather involved study. That's what statisticians do for me. So people in academia were always making comparisons. Usually our method beats up on something. So that's the straw man comparison. In my job, when I see these presentations, to decide whether or not their comparison was even reasonable. So I never really accuse anybody of not telling me the truth, but sometimes I do accuse them of, you're just making a nonsensical argument, which is different. So anyway, so you'd report this. You'd have a couple different panels for this. And there would be 7 of these things right here. You could do that for variance or coverage rate or expectation. I just want you to report more than just one thing. So if you're going to report like a mean or a mode, that's a point estimator, and statisticians want to know more. They want to know something about the variability. That could either be variance, could be some other measure. Coverage rates kind of relate to that because you're building an interval. So have at it. Have fun with it, and try to do things that are kind of sensible. Okay, so that was a long answer to your simulation study for the beta prime. Probably don't do it. You know, what I would do is I'd go to Wikipedia and grab these estimates. And then all I need to do is just compute this thing, alpha tilde, beta tilde. That couldn't be easier for each sample set. And then just report these, and I'm making box plots out of these right here. If you have your code set up real nicely where you simulate all your data, and then all the methods have access to that, it's probably pretty straightforward to do that. And then the whole exercise is just making the plot nice. Spend a lot of time making graphics. So spend a little bit of time on the graphics. Try not to hand me, you know, if you've got 28 configurations or something, try not to hand me 28 full-blown plots, you know, and definitely do not give me, for each method, so I've got 28 times 3, don't give me one box plot on each plot. I hate that, because I can't see them next to each other and make a visual connection. So plots are supposed to be things that I can glance at and go, I see there's some differences and some similarities here. What does it all mean? You know, something's obvious about them. We won't try to piss off Tufte. Do you know who he is? MIT professor that told us all about mistakes of graphing. So I still like Tufte's laws. Okay, midterm problem 4, why not? So I think most people were able to apply the delta method. This was the delta method question, right? Well, let me just take a moment. I said a lot of things. Any questions or comments before we move on to midterm question 4? Sam?
Just for part to problem 2, for the non-bootstrap realizations, you just want to
Yeah, that's right. So you could make it a trillion if you'd like, but you'll spend more time in your code. The real question is what's the smallest number you can make it, and the estimates that you get out of it are stable. So if you crank up your bootstrap replicates, and the thing that you're estimating to maybe 2 decimal places isn't changing, you could crank it up even higher and it won't mess you up, but it'll be a wasted effort. So yeah, you pick B, you're supposed to pick B big enough so that the answers you're reporting are stabilizing. So you do get a full distribution out of the bootstrap. We don't need it to be so big that every little thing in that distribution converges. You're just going to want the things you report to converge. But I'll give you a rough rule of thumb. If it's under 1,000 or so, it's way too small. So I usually start thinking like, I want that thing like at least like 1,000 or 10,000. So this is In Young Kim's favorite question in all colloquiums. Tell me bootstrap replicates. And people will come in and they'll say, oh yeah, I did it for 100. And it took a little bit of time because I had a whole bunch of them to run. But then I went in and I doubled them all to 200. And then she says, it's not enough. And she's right. So make sure if you're doing an iterative approach that converges, you're monitoring the convergence. So the exact same conversation we had about CapJ right here. So if I want this thing to converge in the Bayesian analysis, I need to sample CapJ times. If you were to do it this way, bootstrap, you're forced into doing it that way. So yeah, same exact conversation. So you'll probably say, I found that Cap B is this number seemed to work pretty well. And so I experimented it with a couple different examples, P small, P big, P in the middle, and it seemed to work. And so I used that Cap B throughout the remainder of the study. And that's what you would see in a paper. They usually have some little note. This is how we pick Cap B, and it's usually because an editor asks to say something about it, please. I find it a little bit interesting because you guys are familiar with like Newton-Raphson. So I get questions all the time in my simulation studies. How did I check convergence? What did I do? So now I just add a sentence. Sometimes I leave it out because I'm waiting for the editor to ask me because I'm like, I did all the things I'm supposed to do, of course. And I put it in and it makes them happy. So it's kind of a psychological game. So, oh sure, I'm happy to do that. You know, you've got to do something that they ask you to do. But for like things like Newton-Raphson, I've read a lot of applied math papers. I've never heard somebody say, how do you know that the number of iterations you ran it for brought you into the contraction map? So it doesn't happen. So, but it's the exact same thing. How many times did you iterate this and how did you check convergence? So in our field, we still test review with that. So in other fields, they assume you're, you know, operating at least at a teenage level and you did things at least remotely reasonably. Again, another metaphor. So, okay. Midterm problem 4. So a lot of people had the right idea here, and it was just when I kind of said, how do you apply the result? So let's remember what delta method says. And I think a lot of people reconcocted like what the delta method says for this, and I said, that's not how you apply it. -3 or something like that. So again, very easy to fix up, but some of this theory can be used for things. And so how would you use it? It's not exactly what the theory says, it's close to it. And so delta method says something like this, that G of, I'll say X bar, something normally distributed, whatever it is. And so what I gave you was normally distributed. So it turns out it's just this thing. Some of the xi's, yi's over some of the xi squared. I did notice a lot of people had some funny cancellations in here. These x's will not cancel those. They're just different. So it happens. So does anybody recognize this estimator? I didn't come up with it out of nowhere. I guess I do know what you did, Emily. You saw my last year's exam and I did something slightly different to it. So I threw in a little bit of a red herring that I gave you something that was normally distributed, but it was heavily, it's actually, I think it was unbiased, but the variance was all mangled on it. And I was doing that to make a point, but it really confuses people. So I decided not to do it to you guys. This is the same thing as X transpose X inverse X transpose Y. So in the multi-dimensional regression case, you can load your X's up with your columns of your X's. Y will be a vector. In the scalar regression case, so the simple linear regression, this is that. So they're the same thing. So this is normally distributed. I think you guys all know this, but what you're supposed to say is it's a linear combination of normal stuff, so it's normal. Some people went through and did moment generating functions and all kinds of stuff that I guess it's impressive in some sense, but the problem could have been a lot easier. So it's linear combinations of normal stuff, and we know that those are normal. So anyway, a lot of people did a lot of stuff with the delta method, and then they got down to this last part, and the question is how do I apply, I'll call this thing theta, and so that's theta right here, and so how do you apply the delta method to estimate this creature right here? Where you've got an estimator of theta, that's theta hat, not theta. It's this thing. So I've got an estimator of theta, and I want to estimate this. The delta method says something. The delta method says that this thing right here is converging to a normal distribution. Would that mean e to the theta is its own derivative? This is squared right here. So, and then I've got my variance of theta hat right here. So that's what the delta method says right here. So I come up with this variance of this thing, and the variance is X transpose X inverse times 1/sigma squared. So times sigma squared. So you should have gotten that. So this thing was just X transpose X inverse times sigma squared in this problem. And sigma squared is presumably given to you. So Some people have ends and stuff like that floating around in this, but this really is kind of acting like your ends. So if you had just intercept in your model, if x's was just a column of ones, think about what this thing is. Sum of the squared numbers, 1 squared is 1, so this is n, if we had to intercept in the model. So just something to think about. So you're going to have this. That's true. Some people regurgitated this to me, but that's not an application of the delta method by telling me this thing is kind of like that. So what I would do to apply is I would say we would estimate using E theta hat. So that would be my estimate of G theta. But we're statisticians, and this says a little bit more. So I might say something which is approximately normal. And I guess you could prove that. You could invoke the delta method. I didn't ask you to do that. I just said apply it. And so it's approximately normal in the variance is this thing right here. With variance this, and this is a little bit, I'm going to make a mistake first. I'll just be more clear. Inverse times sigma squared. If you try to apply this, you can't, because you don't know theta. So this is the whole thing, I know, and Parole's going to forgive me for this. Again, it's just driving home a point, and we can get all those points back and still get the grades we want. So you can't apply this because you don't know theta. There we go. So I would just say this. That was a perfect answer to me. So, well, I would just estimate it using this. And then I would say something about how it's distributed. It's approximately normal. We'd probably use that normal approximation. But I need to define the variance, and it would be this thing right there. So, and I would know you did the, oh, this is squared, right? The part that I always forget. So you would square that right there, and you would report this back. And that's how you use the delta method. It doesn't tell you that until chapter 10 of the book, and that's why I'm building it in sooner. And it's built in through your homework assignment too, that you're applying the delta method. So you're taking, and that's what that notation is, P, you're setting it equal to where you see the P's, you replace them with P hat, that's the same sort of thing right here. So this would be equivalent to me writing this. Theta is equal to theta hat. So that's my notation in this case, that I'll just substitute that in, or I can just substitute it in and be done with it. So that's how you apply it. You just use it. And then you kind of know something about that distribution, if you wanted to build a confidence interval or something like that, whatever you wanted to do with it, now you can do that. But you have an actual distribution, you can base all of your probabilities off of. So that's it. So again, not good enough just to know some of the theory. I am impressed if you can do the Taylor expansion thing. And a couple people were just dying to show me that they knew how to do it, so they spent their whole test writing out the proof to the delta method. That's not what I mean by apply. So there's a difference. So there's kind of the theory side of being a statistician, and then there's something that you do with it, kind of the engineering side. We want to blend both of those. Is that helpful? So I gave you the answer. So, but the most important thing is you understand. So good. This is called pivoting, by the way. We'll see it when we get into chapter 8. So, no, chapter 9, intervals. I'll say a little bit about it. There's a lot of different types of intervals out there. I'm going to spend a lot of time trying to dispel some of the issues in testing and telling you what people are fighting over. We'll prove some stuff along the way. Learn some theory, and then we'll understand, hopefully, what do you do with it? So there is a disconnect in these classes that we have You're gonna feel that disconnect as soon as you pass your QE, and you're gonna be like, I know all this stuff, and it's like, okay, good, just put that in your back pocket. Now we need you to do all kinds of stuff. So with it, and I find that that's usually a struggle at first. It's like, I got really good at solving homework problems and working out math, but now I need to do things. So we'll try to prepare you along the way. Any questions? Give it a minute. Homework assignment part, I still haven't posted the problems yet. Still wanted to give you another day to work through it, but they're coming. Try not to overwhelm you. Anyway, keep working on the simulation assignment. And you should learn a lot out of it. Try to turn in something that's about 5 pages. That's kind of what I'm thinking. It shouldn't be a book. Okay. Good. Thanks, you guys. This is the part when I turn off the camera and I'm getting ready to go that you guys all lunge at me.